So we'll now look at an example where we use information on both the derivative and the second derivative of a function to sketch its graph in a reasonable way. So the example is as follows. F of x is equal to 2 arctangent x plus 1 over x. And here it's kind of clear that x should not be 0. So that's taken out of the domain. And we know that the arctangent is defined on all of R. So you could say that df is then R taken away, 0. That's basically what we mean by that. Now, our goal is to sketch the graph of this function as well as we can and get whatever information we can on it. And we can notice immediately that f is a continuous function. So it's continuous on all of its domain because it's the sum of two functions that are continuous on all of their domains. And for the same reason, f is differentiable. Now, usually I say you should check differentiability by computing the derivative. So let's just do that to be sure. So this is 2, 1 over 1 plus x squared minus 1 over x squared. So we see here that the derivative is defined on exactly the same set. So f was differentiable on all of this. So before we do anything, let's make a computer plot of this function. So it feels kind of silly to use this ancient graph sketching techniques when we have computers these days. So what did we have? So we had 2 times np arctan x plus 1 over x. And I mean, what can we see here? So it seems that we're below the x-axis here. Maybe we have a horizontal asymptote in this direction being 0 or not 0. I don't know. We seem kind of flat here. And I don't know if we are all the time going down or if we're going a little bit up first, but then we move down here. Here it may appear from the plot that we have a local minimum. And then we shoot up here to get a local maximum here. Then we go down again, perhaps monotonously. So I don't know if we have a local maximum here or not somewhere. And it appears that we're going to an asymptote here. And of course, when we now do the graph sketching, the point is to get more detailed information on this. So this plot can only ever give us an indication of how the graph looks. And this is why we want to do the graph sketching. So here we've computed the derivative. Let's also just, well, let's find a better form for the derivative first. So we try to have him on factored form. So let's put all of this on a common denominator. So this means here I have 2x squared minus 1 plus x squared like this, divided by 1 plus x squared. Opening up the parenthesis here, this 2 gets killed by him, so I get x squared minus 1 divided by all of this, meaning I have x minus 1, x plus 1, and all of this thing here below. So I see that my stationary points are at plus minus 1, and then I see that the derivative is not defined at 0, which is not surprising. So before I make a table of signs, let me compute the double derivative. And now notice this point of strategy. I'm not going to differentiate this expression. While this expression is the best for seeing the sign of f prime, it's not the best for computing the derivative of f prime. This expression here is much, much nicer. So I'll differentiate him. So here I'm getting 2, and then the derivative of x squared, 1 plus x squared up here, which is 2x. I'm using the quotient rule. And then down here, I'm getting him to the square. Or rather, I was using the reciprocal rule, you could say. So I was using the fact that 1 over g prime is equal to minus g prime g squared. And here, I can use the reciprocal rule again if I want, or rather, I can use what I know about differentiating x to some power. If I differentiate x to the alpha, then this gives me alpha x to the alpha minus 1. And here I'm differentiating x to the minus 2. So I should get minus 2 x to the minus 3, which gives me here this. And again, since I'm ultimately after the signs of this guy here, I put this on a common denominator. So what does this give me? It gives me minus 4x times x to the third, so that's minus 4x to the fourth, plus 1 plus x to the square, and then divided by a bunch of stuff down here. But let's try to simplify up here a little bit. So I'm having here 4x to the fourth plus, and I can multiply this out, so I get 2 plus 4x to the square plus 2x to the fourth. Same stuff down here as always. And then I can see that this guy kills this guy and then turns the plus into a minus. So this is what happens. And now I can move the 2 outside and even the minus. So I'm getting minus here. And then I'm getting x to the 4 minus 2x squared minus 1 like this. And then 1 plus x to the square x to the third. How do I deal with this guy? Well, notice here, so I have x to the fourth minus 2x to the square minus 1. So here I can put x squared equals to u. So I'm getting u to the square minus 2u minus 1. This is a second degree polynomial. I can complete the square here if I want. So this gives me u minus 1 to the square. I have to subtract 1. So I'm getting a minus 2 here. And then I can use the conjugate rule. So a minus b, a plus b is equal to a squared minus b squared, with this being a and the square root of 2 being b. So this gives me now u minus 1 minus square root of 2 times u minus 1 plus square root of 2. And I can then plug in x squared again. So I'm getting here x squared minus 1 minus square root of 2, and x squared minus 1 plus square root of 2. So keep in mind, I want to have this on factorized form because I want to know how the sign acts. Like this. And here, well, there's a lot going on here, right? But here we can notice that square root of 2 is bigger than 1. So all of this is a positive number, and x squared is always positive. So all of this is positive. So this factor here will never have a 0. It will just be positive. So this factor here is completely uninteresting to us. This factor, on the other hand, is x squared minus something negative. So here I can use the conjugate rule again. So this thing there, and I can write this as minus 2. And then I open him up. So I have x minus the square root of this. So 1 plus square root of 2. And then x plus the square root of all of this. Then I just keep that guy who I absolutely don't care about now. And down here I keep what I've had for ages now. So now I have information about this guy. And I have information about this guy. So I have both on factored form. So now I can make my table of sign down here. So let's begin here at the top. I'm going to scroll a little bit. Let's make it a bit long. So in order to have the table of sign of the derivative, we need x minus 1, we need x plus 1, and we need, well, we have the x squared there, so let's do 1 over x squared. This guy does stuff at 1, and this at minus 1, and this at 0, right? So here I'm getting a lot of minuses, 0, and a lot of pluses. Here I'm getting a lot of minuses up to here, and then a lot of pluses. And this guy here is positive everywhere, but he's getting a 0 here, but that's in the denominator. So we'll put a skull just to remember that something bad happens, like this, and going even a bit down. So together they give the sign of f prime. So here we have plus, we have 0, here we have minus, here we have the skull, here we have minus, here we have 0, and here we have plus. And now we can use the corollary to the mean value theorem to see that here we go up, here we go down, here something bad happens. I don't know if it's an asymptote or not, so I'll just do something like this. Here we're negative, so we're going down again, and here we're positive. And now we're going to figure out what the double derivative does. So we just need this line here. So the double derivative is now x minus the square root of all of this nonsense. It's x plus the square root of all of this nonsense. This was positive all the time. And then we have this guy who we can marry with him to get minus 2x to the third like this. This thing here, well, it's bigger than 1. So the square root of this is bigger than 1. So we have here this nonsense. And here we have minus this nonsense. And this guy here is 0 here. And this guy is 0 here. It's negative here, positive here, and negative like this, and positive here. And this guy is giving us the skull here. And for negative x is positive, and for positive x is negative, like this. What does this tell us about f double prime? Well, he's positive here, 0, and then negative here. We're getting the skull here. So, I mean, we already know we're badly behaved at the origin. Then we're positive here, 0, and negative. What does this tell us about f double derivative? Well, that f double derivative is increasing, decreasing, increasing, decreasing. What does this tell us about f? Well, here that he is happy, so convex, meaning that the slope is increasing. Here is unhappy, here is happy again, this was a 0, and here is unhappy, like this. And now we can see, so does this match the information we have here? Well, kind of. So if we now try to combine this and this, then what do we see on f? So we're increasing here, being happy, we're increasing being less happy, and then we have our maximum point here, and then we're becoming less and less happy like this until we reach, so here is the thing, until we reach here. So we don't know if we're diving into an asymptote here or we're diving towards some point. And then here, so decreasing with the slope becoming larger and larger and larger, we're having a minimum point here. We are gaining altitude after this, like this, and here we're starting to become more and more sad. Now, of course, I don't know if I should move this up or down. I have no idea about this. So let's keep it like this for a while. So what I notice here is that I have a local maximum here. I have a local minimum here. I should check their values. I can note that I should check the asymptotes here and here. What are they? So I should check the limit of the function. And I should check the limit of the function here and here. So I'm putting question marks here. So in a sense, I've now made a very careful table of signs for both the derivative and the double derivative. This does not tell me everything because clearly I have a lot of question marks here, but it does give me a complete overview of the information I need to collect in order to get a clear image of what's going on here. So let's start doing this then. We only need this thing now. So let's recall the formula for the function. Now let us go a little bit up here. So first of all, what happens as lim x tends to 0 from the right, let's say? Well, this guy tends to 0, okay? So arctan is 0 at 0. And this guy here, well, if x tends to 0 from the right, it gives me a plus infinity. So here I'm getting plus infinity. What happens if I approach from the left? Well, I still get 0 here, but now I get minus infinity here and minus infinity here. So this means I can take away these question marks, and I do know that I have a vertical asymptote here, and why not just denote this by making a stapled line like this? So that mystery is now solved. What happens when I go to these limits here? Well, the limit as x tends to plus infinity of f of x, what is this? Well, now these guys play not an opposite role, but slightly. So 1 over x when x tends to infinity gives me a 0. Same when x tends to minus infinity. What about the arctangent? Well, the arctangent, what is his job? Well, he's supposed to take, so remember the tangent, he takes an angle and gives me the slope of the line from the origin with that angle. So if I have here an angle x, then the tangent will give me the slope of this line. The arctangent does the opposite. So he takes the slope here and gives me the angle. So what angle gives me slope infinity? Well, slope infinity is the angle 90 degrees. So pi divided by 2. So this, when x goes to infinity, tends toward pi divided by 2. I get the 2 here. So that's pi. What happens when x goes to minus infinity? Well, if we have slope minus infinity, so that's the angle minus 90 degrees. So minus pi half, and 2 times minus pi half is minus pi. So if I go to minus infinity, I'm getting a minus here. If I go to plus infinity, I'm getting a plus here. So this thing here goes to pi, and this thing here goes to minus pi. So now these mysteries are solved. So here, plus minus pi. And then finally, what values do we have here? So we can now compute f at 1. So that's 2 arctangent 1 plus 1. Now, again, so the arctangent takes the slope 1 then and gives me the angle. So what line here has slope 1? Well, that's if the angle is 45 degrees, so pi divided by 4. So this is 2 times pi divided by 4, which is pi divided by 2 plus 1. And similarly, if I take f of minus 1, get 2 arctangent minus 1 minus 1 over, or plus 1 over minus 1, which is this. And what angle gives me the slope minus 1? Well, that's minus 45 degrees, which is minus pi divided by 4. So here I'm getting minus pi divided by 2 minus 1. So here I'm getting pi half minus 1, and here I'm getting minus pi half minus 1. That was supposed to be a plus. So mystery solved here as well. Numerically, what is this? So pi is more or less 3. So this is 1.5. So this is more or less 2.5. And what is this thing here? So this thing here is more or less minus 2.5. So does my sketch here look convincing? Well, not really. So what I need to do is I need to move this down quite a bit like this. Let's move this guy down. So, well, even further, I guess, like this. And now we can compare to the plot again. So here, well, we did have horizontal asymptotes here and here. Now we know their values, pi and minus pi. We do have a local maximum here and a local minimum here. And we now know that this is at minus 2.5 more or less, and this is at 2.5. And then we know that here we have a vertical asymptote, and here we're going to the vertical asymptote. And we know that the straight line here is just an artifact. And we know that there is no local minimum here and no local maximum here. This was also just an artifact. And if we ask Python to plot with higher accuracy, then we see that, well, now this looks more like an asymptote, but you see, Python is insisting to connect the dots here, okay? And that's just the way it's put together. So it's hard for us to stop him. But now that we did this with more accuracy, we're going higher up now to 300 and minus 300. And this is kind of masking a bit the behavior here. So now we're absolutely not able to discern a local maximum here, a local minimum here. If we go back to our crude sketch, these features were super visible. So that's it.